So for PMOS, we saw that in the previous slide. It's okay, we can just redraw it. That VGS was equal to, this was gate, this was source, and this was drain. VGS was nothing but minus VDD. VG is 0 and source is VDD. So 0 minus VDD is minus VDD. And VDS, this is nothing but my output, is nothing but Vout minus VDD. Now let's find out whether the transistor is on, off, and in linear or saturation. So VGS is VDD, so minus VDD, we have to find out first the transistor is on or not. So VGS dash VTP. VTP is a negative value somewhere like 0.6 or 0.7, and this is minus 1.8. So with sign less than. So transistor is on. For PMOS, if VGS is less than or equal to VTP, then the transistor is on. Now we have to find out whether it's in saturation or linear. VDS dash VGS minus VTP. Let's quickly do VDS. Here is nothing but Vout minus VDD. This is what I've written. VGS is minus VDD minus VTP. We all agree that VDD, if this VDD I take on this side, it will be plus, so it will be cancelled. So it's VO and VTP. And VO, we are trying to find output low. It's nothing but low value. But this is low, but still greater than 0, and this is a negative plus, isn't it? VO low, let's assume it nearly equal to 0. This is minus of minus VTP, that is nothing but plus 0.7. So with sign, correct, less than. So if VDS is less than VGS minus VTP, then the transistor operates in saturation. So now the final thing what we need to do is equate both these equations. ID of N equal to ID of P. PMOS in saturation, NMOS in linear. If you want, I can just write the equation real quick for you. For ID in linear, it's nothing but mu n COX by 2 W by L. Yes, that's correct. Twice VDD minus VTN. Why VDD? Because my VGS is nothing but VDD now. I'm assuming an input high. Into VDS. VDS is nothing but Vout, and Vout is nothing but VOL, because output voltage is nothing but VOL. We are trying to find that VOL minus VDS square, Vout square, which is nothing but VOL square. This current needs to be equated with mu P COX by 2 W by L VGS minus VTP, and VGS in this case is nothing but, we just saw for PMOS, minus VDD minus VTP the whole square. I'm sorry, this is square, isn't it? And this is going to be mod value. You have to just solve this and you'll find the value of VOL. And when you write the final expression for VOL, you don't have to worry, you don't have to get intimidated. I just want to show you, and no one is expecting you to derive this in the exam as well. What we want to only see here is VOL, when we write the final expression, it's nothing but VDD minus VTN minus square root of VDD minus VTN the whole square minus beta n by beta p. Beta n and beta p is nothing but mu n COX W by L. Beta p is nothing but mu p COX W by L. Beta n by beta p into bracket VDD minus mod VTP the whole square. It's just a simple quadratic equation which you need to solve. What I only want to draw your attention here towards is the VOL value depends on the ratio of beta n. VOL depends on the ratio of beta n and beta p. Is that clear? And this beta n and beta p in turn is dependent on W by L of n and W by L of p. So your final VOL, higher or low, will depend upon the ratio of beta n and beta p, which is directly proportional to W by L. So this is also called as ratioed logic. I hope you understood why it's called ratioed logic. You also understood how to draw a pseudo NMOS inverter, NAND and NOR, and how does it work. And you also understood the drawback of ratioed logic is that it cannot produce a perfect VOL. Perfect VOL means a perfect zero value at the output, and there will be a value which will be greater than 0. It would not be a perfect 0, and that value is nothing but after you substitute all these terms in this equation. It was not complicated, guys. It was very simple. Don't take so much of tension. Just understand that ratioed logics are called ratioed logics because the final low output depends on beta n by beta p, which in turn is depending on W by L ratios. And depending on that, we can understand where I can get my output value to be. So I hope you have enjoyed it. Stay tuned for dynamic and domino circuits. Take care. Thank you.